There we go.
Mhm.
So there's 29. So I'm guessing each of us do what? About 10 slides.
10. Mhm.
Oh my goodness. Okay. Um, okay, so what is an undirected graph of G? An undirected graph of G consists of a set V of vertices or nodes and a set E of edges or arcs, such that each edge, which E is an element of E, is associated with an unordered pair of vertices. So we denote the graph of G by V and E. So,
Mhm.
oh, this is like related to computer science. I get this. So
Mhm.
this is undirected and this one's directed. So like I'm guessing because it doesn't have the arrows and whatnot, and this one does. So directed, undirected.
Mhm. Yeah.
Okay, so let's see. So going back to the graphs from up here, I guess, or something similar. A directed,
Directed.
yeah.
Mhm. Yeah.
A directed graph of G consists of set V of vertices or nodes, basically reiterating from this slide, such that blah, 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 blah. So yeah, so the directed graphs are the ones that have the arrows, and then these are undirected since they
Yeah.
don't have arrows. Okay, let's see. In situs, an edge E in a graph of undirected or directed is associated with the pair of V and W is said to be incident on V and W. And V and W are said to be incidents on E and to be adjacent vertices. So V and W, is there a W here?
No, that's V and U. I think
Yeah,
it should be U.
yeah. Incident on E. I'm guessing she meant to put V and W, so I'm guessing this one's W.
It's in the example below.
Yeah.
On X U V W.
Yeah, because right here it says a pair of V
Mhm.
and W. So there's a
Yeah.
V, and then this one should be W.
Yeah.
I know she has some sort of typos on these slides too. But I mean, I don't like overly, but okay. So I'm guessing so since V and U are incident on E, so these vertices are adjacent vertices and whatnot. So example 1, oh my goodness, this reminds me of geometry. So figure an
Mhm.
example of a graph using this graph.
Mhm.
Another example of a graph. Okay, it looks a little different, but okay. So example 3. Okay, so with these, I'm guessing it can be a shape as long as it has like the vertice points. So if you know, like this one,
Mhm.
U, V, X, and W. This one, the same way, kind of like an acute angle. This one looks
Mhm.
like a directed graph. Okay, so an application of parallel computing. So as hardware costs have declined, it has become feasible to build a parallel computer, which many processors are capable of executing several instructions at a time. Graph are good models to describe these machines. So using the parallel computers, this is the 3 cubes. And then let's see. That's another example. So hypercube, each processor connects to 2 to the power of n neighbors in A and dimension of hypercubes. So an example of that is IPSC and cube SGI and O2K. So when D equals 0, then it's 2 itself. Whenever D is 1, it goes down to 1. So D equals 2. Oh, yeah, this is computer science. So like, do you get this one or no? I'm able to explain it if I need to.
0 1 0 0 0. Mhm.
Yeah, no,
The bottom one is 0 1, then it will be 1 1.
yeah.
Like that, right? Mhm.
Okay, so like, let me see. Let me go ahead and add a text real quick.
Okay.
So like with like computers, what was it? So with computers, you use like binary code. So like let's say that is 0, which equals to 1, which is what we have here. And then when you have 0, 1, that equals to 2. Or no, that's 1, 0. So this one will be 0, 0, which is 1, 1, 0, which is 2. So it goes by the powers of 2s. So for like this one, this would always be 1. If like it's like there's a 1 in it, and that would always be 1. So since this one has nothing in it, and this one does, so 2 to the power of 1 is 2. So going on to the next part. So and so forth. Yeah, so like it's a bit complicated after that. Okay, so yeah, so the hypercubic dimension 0 through 4, the processor and the cubes are labeled with integers, here presented as binary numbers. Two processors are neighbors if and only if their binary labels differ only in one digit place. Okay, let's see. What is a complete graph of K to the subset of N? So parallel edges are distinct edges of a graph associated with the vertex pair. An edge incident on a single vertex is called a loop. So a simple graph is a graph with neither loops nor parallel edges. A complete graph on N vertices denoted by K subset of N1 is a sample graph with N vertices in which there is an edge between every pair of distinct vertices. And
Okay, let me go over now. Okay, this will be the example of the complete graph, the one you mentioned about. So the bipartite graph, right? Our graph G equals vertices and edges is bipartite. Bipartite.
yeah,
Is it
it's like a tongue twister.
bipartite? Yeah. If there exists subsets B subset of 1 and B subset of 2, either possibly empty of B such that B1 intersections B2 equals is not equal 0.
Yeah, it doesn't equal 0. So
That doesn't
like
equal 0. B sub 1 union B sub 2 equals B. And each edge in the E is incident on one vertex in B sub 1 and one vertex in B sub 2. So this one is bipartite and this one is not bipartite.
That is so weird. I'm wondering why this one isn't, but this one is.
Yes. The bottom one is also bipartite, right?
Yeah, this one's a complete bipartite graph. This one's supposed to be bipartite, but this one isn't. Maybe because it doesn't connect like all the dots like this one does. That's what it kind of looks like it, right?
Yeah,
Or
it's
should I like
kind
it?
of similar, but not exactly.
All right, let me go ahead and slide down.
Complete bipartite graph. The complete bipartite graph on the M and N vertices denoted by K sub M N is a simple graph with vertex set is partitionized into sets B sub 1 with M vertices and B sub 2 with N vertices, in which the edge set consists of all edges of the form B sub 1, B sub 2 with B sub 1 elements in B sub 1 and B sub 2 elements in B sub 2. So this will be the example of the complete bipartite graph. So what is path? Let B sub 0 and B sub n be vertices in a graph of path from B sub 0 to B sub n of length n is an alternating sequence of n plus 1 vertices and n edges, beginning with vertex B sub 0 and ending with vertex B sub n, in which each edge is E sub I is incident on vertices, B sub I minus 1 and B sub I. So here B sub 0, E sub 1, B sub 1, E sub 2, and so on. So P sub 1 will be, is this B1? B sub 1, right?
Yeah, so I'm guessing it's going by like the vertices and the edges. So
Mhm.
with this one, yeah, vertices 0. So you start from like the beginning and then so forth. So like this one is like a good example of P2 right here. And then like if it goes on and for like for 3, then we go down to here and then to 4 right here, but you still have to follow the same formula right here. So for this, since it goes up to V2 using this formula, then this is actually P3.
Mhm.
Okay.
Okay, so finding all paths from 2 to 3. So here below are all paths from 2 to 3. 2 to 3.
Mhm.
Is this 2 is greater or equals? Or is this only the arrow?
So like
I
this,
know.
yeah, no worries.
Yeah.
Like it's so familiar with me because I've actually had like a couple of courses where we had to like go
Oh.
like stuff like this and we had to like compete it ourselves. So
Mhm.
that was I liked it, but not a lot of people like.
I'm not on this part.
Yeah, no. So like to find all the paths from 2 and 3, so we will have to like figure out what inputs basically. The inputs are like 0, 1, 2, and 3. So we have to figure out like what goes to 3. So let me go ahead and zoom in on this real quick.
Okay.
And so like right here, let's say you start with 0, but what inputs really do go to 2? So whatever goes to 2, you have this right here. So that's why this goes to 0. But you still have 3 right here. So then this is a good example of the middle one right here.
Oh yeah, 2 goes to 1 and 2 goes to 3.
No, so
Oh,
like
1 goes to 3, right?
yeah, so
Okay.
like this one right here. So 2 goes to 0, but it also goes to 3.
Yeah, okay.
So then you'll go back to 2. So 2 right here, it goes to 1, and then it also goes to 3.
Oh,
And then for the last one right here,
you
you still
goes
have
to
2,
zero,
it goes to 0, and then it goes to 1, and then
1
it goes to
to
3.
3.
Yeah. So
Okay.
that's why it says like from past 2 to 3. So you're gonna start at 2 always. But what are the different paths that takes you all the way to 3?
Makes sense.
Trying to
Yeah.
get it? Yeah.
Mhm.
Okay.
Okay, remark in the absence of parallel edges in denoting a path, we may suppress the edges.
Mhm.
Okay, so connected versus disconnected graphs. A graph is connected if every vertex is joined to every other vertex by a path. Then a disconnected graph is a graph that is not connected. Very simple. That this one is connected and this is disconnected. So it looks similar, right?
Yeah, I'm like looking at it right now, trying to see what's the difference, but they look the same.
Yeah,
Yeah, it looks the same. But I don't know, is it?
I think
Let me see.
the first one looks connected. Everybody.
How is this one not a connected graph? Like, I mean, I would get that it's connected graph by like the vertex by a path. So like everything from like this triangle to this triangle is connected. But what's disconnected is this side right here, which oh, I see it, I see it, I see it. There's like a dot right here.
Oh, yep.
It's so hard to see. I'm just like, wait, I see
Yes.
something.
Yes,
Okay,
yes.
so basically it has to have a vertex point.
Oh, yeah. That means the first one is connected to every single one, but the
This one isn't.
other one down here.
Yeah. Oh, that was so hard to see.
Yeah.
I'm like, how is it different?
Yep.
And so like for this one, I
Is the
guess
graph connected or disconnected? So
it's
looks like
disconnected, isn't it?
connected.
Because like it's
Very
also
hard
have like,
to
yeah, no, because like going
distinguish.
back to like this graph right here, you have a vertex
Mhm,
point where like it crosses through.
mhm.
And these, you don't even see any points that crosses through. So for a graph to be connected, it has to be
Right.
joined to every other vertices by a path. So these are
Mhm.
crossing each other's paths, but they're not connected.
Yeah, that
Like,
means disconnected, right?
yeah, that's the way it looks like to me. Because this one says it's disconnected, and this
Mhm,
one passes through, and
mhm.
it looks so much like this one, so it has to be disconnected.
Okay, and
Okay.
let's go to other side.
Mhm.
Here is connected versus disconnected graphs. So first one is connected, right?
Yeah, the first one's connected.
And A is connected. Both are connected, right?
Yeah, both of these
And in figure B, this looks
disconnected.
disconnected, right?
Yeah,
And the C one also look disconnected or
yeah,
connected.
disconnected.
Disconnected.
Yeah, so like I'm remembering like if like it passes through and there isn't like a vertex dot like
Mm-hmm.
these are, then it's gonna be disconnected. But this,
Disconnected.
yeah,
Okay,
yeah. So this one right here is for sure
it's
connected,
connected.
but these two are disconnected. Okay.
Graph. Let Z equals V, E be the graph. We call V subgraph of what is this V? VE? What's
V,
that?
I think that's supposed to be V
Apostrophe
naught, V
V
naught,
naught?
V naught.
Is
That's what
it
it looks
not?
like to me. Yeah, that kind of looks like a knot to me. We
Okay,
call
then
these,
V naught, E naught, or subgraph of G if V naught. Oh,
oh my goodness.
what this sign is
Um,
kind of hard to find out.
that is a subset.
Of subset of B and inner subset of E.
Mm,
I think here is subgraph of E.
where?
I mean, V naught subgraph of B or subset because our topic is subgraph.
Oh my goodness. I
I'm
barely
just guessing.
understand. I barely understand it. What is she trying to say? Oh my goodness. Okay, let's just, I mean,
Let's jump to number 2. For
yeah.
every age, E naught element in E naught, big, I mean uppercase E, if E is incident on V naught and W naught, then V naught, W naught of elements of V naught. So the graph G1 and G2, graph G1, V1, V2, V3. Oh, the first one is just a graph and the second one is subgraph G, subgraph of G.
Yeah, so this one is supposed to be a
One,
subgraph of this one.
V2, V3, and V4.
Because,
Graph G is a subgraph of G2. Okay, graph G is a subgraph of G2 is isomorphic to G1. Then function.
this one I might actually have to double check in the videos.
Okay.
Yeah, because I know that she's posted like lecture videos on that. They kind of help, but yeah, they kind of help, but yeah. No, I do not like
It's
that graph.
very hard to read the graph, right?
Yeah, it kind of sounds
Easy
like
to
you're like
understand,
copying
but
foreign or looking at a foreign language.
yeah,
Okay.
that's what we are having now.
Yeah.
We might have easy to, I mean, we can understand easily, but it's hard to express, right? Express verbally.
Yeah, even like saying like some of like the words in there, like it's like a tongue twister, like bipartite. I don't know if
Yeah,
I'm saying that right.
bipartite, yep.
Yeah. Okay, so we got
Applications of subgraphs chemistry. Well, how can we read this? A data set of molecular graphs.
let me go ahead and zoom in real quick.
Okay, they looks like this. And frequent subgraph mining. Our frequent subgraphs pattern are on the right side, and on the left side are data set of molecular graphs.
No, I'm not liking this. I'm not liking that at all.
Yeah, it's very hard to explain.
I
You can
haven't
figure
been
it
in
out, but
chemistry. I haven't been in chemistry since high school. How am I supposed to remember how to break that down in math form? Oh my
it is a
god.
form that
This is-
occur in at least one of given graphs.
We'll go with that.
Okay,
Oh my goodness.
component of a graph. Let G be the graph and B be the vertex in G. The subgraph of G naught of G consisting of all edges and vertices in G are contained in some path beginning at V is called the component of G containing V. There are two connected components in above undirected graph 0, 1, 2, 3, 4. So 1, 2.
Okay.
Okay, these are the undirected graphs, right?
Yeah. This one I totally get.
Okay, yeah, go ahead.
Yeah, no, I totally understand this one. So let G be a graph, giving be a graph from B vertex in G, the subgraph of G naught of G consisting of all edges and vertices in G are contained in some path beginning at V is called the component of G containing V. So what's V? Oh my god.
Vertices?
Yeah,
The vertices.
okay. I might have to look at that video. Yeah, no, no, I'll stick to computer science. No. Oh my goodness. Okay, so I think it was
Let's
this.
to-
Yeah, here we go. This one is only 10 slides, so what?
Three
Yeah.
diagrams.
Yeah.
Okay.
Okay, so trees. A free tree of T is a simple graph satisfying the following. If V and W are vertices in T's, there is a unique simple path from V to W. So, okay, so simple. So basically an actual tree, a free tree. So A, B, C, D,
Mhm.
E. But this one is not a tree because it connects like that.
Yeah.
This is not a simple tree. That was simple. Okay.
Yeah.
A rooted tree. A rooted tree of T is a tree in which a particular vertices is designated the root. Well, of course, I mean, I call that the main, but okay, we'll go with root. And then let's see. Trees application. So this one is the root of the Wimbledon champion. So graph is the champion, and then you have the tree that follows along, but it's still a simple tree. Yeah.
Now let me go over
Mhm.
trees and its parts. The level of a vertex B is the length of the simple path from root to V. The tree data structure. So this is a this is a tree data structure from A to B, from A to B, A to C, then C to F, C to G, then B to D, B to E, D to H, and D to 1. Okay. A is the root, and F and G are the siblings. D is our parent node. H is child node, and I is link node. Okay, this is our tree data structure, right?
Yeah,
Yeah,
if I were you, I would remember that because I get the feeling this is gonna pop up in the test, the final exam, or on the quiz. And she doesn't just have it all pointed out like that. She normally doesn't really focus that much on that, but get on it.
Okay.
Yeah, no, like I understand it. I mean, it's like the parent node and the root sibling node. Yeah, I've worked with that.
Okay.
Yeah.
Okay, subtree.
There we go.
The height of a rooted tree is a maximal level number that occurs. So here P is the root, P is the key, and P goes to Q and R, Q goes to A and B, which they are siblings, and R goes to C and D, and C goes to M, and M, and M goes to H and I. H and I are the lead nodes. So on the other side, A goes to L goes to E, F, and G. Okay, so here are three, right?
Mhm.
L is a parent and E, F, G are the children. So this triangle is the tree, subtree.
Yeah.
Right?
Yeah. So this one. So this one has 4 levels. Yeah. So with the root being level 0, and then Q and R is level 1. A, B, C, and D are level 2. L and M are level 3. And E, F, G, H, I, they're level 4.
Yes.
Yeah. Okay. I remember that.
One more slide.
Yep, that's our last slide.
Cyclic versus was that acyclic graph
Acyclic.
and
Yeah.
acyclic? Acyclic?
Yeah.
Okay, cyclic graph. It looks like connected graph.
Yeah, like the connected graph.
And acyclic graph looks like this connected graph.
Yeah, but like this one, you know how like it's not like all like coming to like the center connected like a connected graph normally would. So I'm guessing like it goes back to like the connected graph and disconnected graph. So like this one would be a connected graph. This one, I'm just gonna remember it's kind of like a disconnected graph.
Okay.
Let me look at that one real quick. Let me see. Or let me just look it up on here. That should be easier and faster. With cyclic graph and discrete mathematics. Okay, so let me do this. Subgraph induced by this coloring is a forced. What?
Induced by the coloring. Oh.
So it goes by the color on a acrylic coloring of planar graph. Okay, I am not going to read another 26 pages in that. No. Let me look at some images and see if there's something on there. So, a kilograph and directed. No, let me see.
Cyclic and acyclic are.
Yeah. Oh, let me see. A cyclic, yeah. I don't know why am I calling it acrylic. A cyclic, so cyclic, right? Let me see. Ooh, let me look at the name. Yeah, cyclic. Oh, come on, go back up. Accidentally messed with that. So cyclic and discrete mathematics. So when it's not like directed, but this one's directed, this one's undirected.
Mm,
So if it doesn't all connect into one like this, and it's
Then
cyclic graph.
directed cyclic graph.
This one, if it only goes like one
Mhm.
way, then it's a cyclic. Like it is.
In our lecture note, just go down. Okay, the first one looks like direct.
Yeah,
Right?
yeah, because like all of these nodes are like all connected. But
Mhm.
this one, it only goes down one way.
Mhm.
You see
Then
that?
undirected.
Yeah, like cyclic
Mhm.
is like all connected nodes and vertices, but this one, it only goes down to like one way. While this one has like so many different ways to go. Kind of see? No? Yeah.
Yeah. Yes.
Okay. I'm guessing the rest we could go ahead and leave for Kelsey, assuming that she's still in the group discussion.
Mhm.
Let me see. Because I know that people have been dropping it.
I checked last. I think I checked yesterday. She was there.
Wait, what?
Yes, she was there, but let's check today.
Oh, she was in your class today?
I mean, I saw her name on our group. That means that she must be in our class.
Yeah.
Yeah, she is right.
Yeah, she's still in the class, but that's weird.
I think you can go ahead and stop the recording.
Yeah. Let me see.